Welcome to the James Webb Space Telescope Town Hall meeting. My name is Jason Callery. I'm the project scientist for the James Webb Space Telescope project at the Space Telescope Science Institute. The Town Hall is an event that we circle on our calendar every year. It's our opportunity to tell you the biggest developments in the JWST project and also hear from you and answer any questions that you might have. A lot of the senior leadership of the JWST project is here in the front row today. Before I start, I have a couple introductory remarks. We're going to jump right into the presentations. I want to say that we have a wonderful reception today, and that's being sponsored by Northrop Grumman. Northrop Grumman is a prime contractor on JWST. They've been doing a wonderful job building major aspects of the telescope, and they're also feeding us today. So I want to thank them for the reception. I wanted to advertise an upcoming meeting that we have. Every couple of years, we've had a major international science meeting about JWST. And these meetings have been packed with the exciting astrophysics science case of the mission. The most recent one was about 2 months ago at ESTEC in the Netherlands that the European Space Agency, our partners on JWST, organized. Brought together about 200 astronomers over a broad swath of astrophysics extending from solar system science to high redshift galaxies. And it was really the sense from the meeting that the top questions, the most important questions that face us in most areas of modern astrophysics require the capabilities that JWST brings to the table. It's the high precision, high throughput imaging and spectroscopy in the infrared. That's exactly what's needed to make the next big breakthroughs in these science themes. And so the next meeting is going to be organized by our other big partners, the Canadian Space Agency, and this is going to be a meeting in Montreal, Canada in October 2016. We're going to be providing a lot more information about this meeting as we go through 2016, so please consider attending this meeting if you want to get an idea of the latest JWST science case. So we have 4 presentations today in this town hall session. We're very excited about 2016. We are less than 2 years from the Cycle 1 call for proposals for JWST. And the conversation on JWST for well over a decade has been about the hardware and the engineering and the schedule and the budget, but the science is right around the corner right now. So we're going to have a presentation from the program director, Eric Smith, on the status of JWST and how the mission is going. And then we're going to move on to the science very quickly. So the first presenter after Eric, the second presenter of the night will be Neil Reed. Neil is the Associate Director for Science at the Space Telescope Science Institute. He's going to talk about the science policies and the science timeline leading to the first science opportunities in a few years. The third speaker is going to be Klaus Pontoppidan. He's the Deputy Project Scientist for JWST at STSCI. He's going to be talking about the user-facing side, some of the proposal tools and the data analysis tools and the pipeline development that's happening, the documentation, all of the stuff that you need to plan and get science out from JWST. And then our final speaker today is going to be Priya Natharanjan. She's going to give a science talk on JWST and the first black holes. So that's the introduction for all the speakers. I won't reintroduce everybody. I'll let them go in turn. So Eric, come on up.
Thanks, Jason. I too want to thank Northrop Grumman for sponsoring the event here tonight. What I want to talk about is just give you some status. We'll start off with the programmatic status, things budget and schedule. We'll then review some of the hardware progress, which is very exciting. Got a lot of pictures about that. And then I'll talk a little bit about our role as a community leading into Neil's talk then. Those of you that attended either the NASA Town Hall or any of the PAG meetings beforehand might have seen this budget. The budget along the top is the enacted FY16 budget, and these numbers are the numbers that have been in the JWST budget now since the 2011 replan. And I want to take this opportunity to not only thank all the folks working on the program in the project, our partners at ESA and CSA, Northrop Grumman, Ball Aerospace, ATK, everyone at the Space Telescope Science Institute for sort of holding up their end of the bargain, but also to thank the administration, OMB, and Congress for holding up their end of the bargain in keeping this profile safe. They can change this at any time if they decide they want to have different priorities. The fact that they've kept this a priority is a tribute to both the good work that's going on here and some of the outreach work that you all have done with those federal agencies, so I appreciate that. We have been stable on the budget now for half a decade. We are still on track with our budget, And as part of the replan, we get a yearly review by the Government Accountability Office, the GAO, and this year you see the title of their report up there. This was for folks in Washington who have worked with the GAO. This was essentially a hug and a kiss from the GAO report this year. They have said that we have adequate budget and we have adequate schedule, and they made one small recommendation that is very easy to comply with. So we had a very clean report from the GAO this year. They've gotten better and better each year. So, and that's, again, a tribute to all the folks working very well with the GAO. So we're in good shape when it comes to the budget. We have adequate reserves, not only integrated over the life of the program, but in each year we have adequate reserves, which in NASA parlance means you have about 30% reserves. So the other big thing we want to make sure we have enough of prior to launch is time. So you want to have schedule margin in addition to budget margin, and this chart here depicts how you would use your schedule margin as a function of time toward launch. So at the right-hand side of the chart there you see launch, and if you somehow magically were able to burn your reserve down one day at a time or so, you would be on that blue line. That was the plan that was developed back in 2011. That's how reserve would be used over time. The dashed line is a recommended level of reserve. This is sort of a Goddard best practice. So we wanted to have more reserve because we knew we were a large mission and more complex than most. And then the little gold hexagons there are how the reserve is actually being used. And so you can see that it gets consumed in a quantized fashion, and you can read each time what caused the consumption of the reserve. And so what we want to make sure we're tracking that blue line. So you're either close to the blue line or above the blue line. And we have been now, again, 4 or 5 years. So doing a good job of maintaining schedule and staying on track for 2018. Now, those of you who look at the webcam might have already seen this image here. You see two pictures on the left-hand side. That's the telescope structure doing a test fit to the spacecraft bus out at Northrop Grumman before it is shipped to Goddard, so it gives you a scale. Here you can see a person, and so that gives you a good sense of scale for the whole thing. And this is what the telescope looks like now out at Goddard. 12 of the 18 mirror segments have been installed, bolted and bonded. If you look at the webcam now, you'll see the robot arm is hovering over this position with the 13th mirror segment. So the mirror segments are going on very rapidly. Once the 2 wings are populated, we'll put the aft optics system into this hole here. We'll remove this metrology structure, and then following that, the secondary mirror supports you see here. So the secondary support is up here, and that gets folded down, and then they would attach the secondary mirror. So excellent progress is being made on the telescope this year. Another thing near and dear to all of our hearts are, of course, the science instruments. We've had those in-house for a number of years now, and what you see are some of the torture tests we put those instruments through this year. Here is the integrated science instrument module sitting on the vibration table at Goddard, and so it sees the vibration spectrum that we will see from the Ariane 5 launch. After they do that, they blast it with the sound, the acoustic tests. You can just barely see it up here. This is the woofer, bigger than most of us in the room here. Then they subject it to electromagnetic interference testing, and then this last image is the Ison being lowered into the large thermal vacuum chamber at Goddard. It has been in this chamber now for 71 days. They're on day 71 of a roughly 100-day planned test, less than 3 weeks from coming out of the chamber. And I'm happy to say that they're getting results as expected or better than prior cryo-vacuum tests, because detectors were replaced for the near-infrared imaging spectrograph and fine guidance sensor and the European near-spec between cryovac 2 tests and cryovac 3. So this is going very well. And sort of the remaining activities they have in that test, a lot have to do with how the scripts that are being developed by the Space Telescope Science Institute will run those instruments. They'll be running them with the scripts, doing day-in-the-life type operations, and then a final optical checkout. So for many years, folks may have heard that one of the challenges on the program was the cryocooler for the mid-infrared instrument. All our instruments are passively cooled with the exception of MIRI. It needs a little refrigerator, and I'm delighted this year to show you nothing but flight hardware in this picture. And this is the cold head that sits on the Ison, so this is actually flight hardware that's in the chamber at Goddard right now. This is the compressor assembly that's under cryovacuum testing at JPL, and that is going very well. Here are the associated electronics. They're also part of this test at JPL. And then these are the little holding fixtures that hold the coolant lines that run. Right now, those lines are in this bucket structure down here. So there were many challenges along the way, but we now have a working MIRI cryocooler undergoing its testing. The spacecraft that's going to provide all the infrastructural support for the mission has a bus right here. This is the bus structure. It's undergoing some of its final structural testing before we start integrating all the parts that are flowing into Northrop Grumman now, like the propellant tanks, the star tracker assembly, the star trackers. There's a biaxial gimbal assembly in this configuration, getting cryovacuum tested there. So that's another large activity that's going on this year. All those parts are going to be flowing into either inside the cone of the spacecraft, outside of it, and they're also building up the panels that go on the side of it that house all the avionics and electronics. And then, of course, one of the iconic features of Webb is the sun shield. And on the left-hand side here, we see this is engineering hardware that is out at Northrop Grumman. Here you see the engineering unit fully deployed. An elated Bill Oakes, project manager, right there in the center. And this is that same sun shield folded up. On the right-hand side, this is flight hardware, one of the pallets that you see here that contain the sun shield, and this is flight layer number 4 for the sun shield, 4 of 5. 2 of the 5 are delivered, and they're out at Northrop Grumman now, and the remaining 3 are in various stages of manufacture just outside the Marshall Space Flight Center in Huntsville, Alabama, and they'll be coming in later this year. Another big activity in 2015 was actual testing of the test chamber down at the Johnson Space Center as we get ready to test that flight telescope in Science Instruments in 2017, sort of a year from now. Here you see the setup inside the very large chamber A. This is the this is the Pathfinder telescope with the flight aft optics system in the center of it there. So the tertiary mirror is down here, the fine steering mirror is up right about there. And this is a picture of a Ball Aerospace employee on a diving board out over that structure, taking a picture of the secondary mirror, and then himself down there on the platform. Cool picture, but there was a very successful second test of this equipment and the chamber and the procedures down at Johnson. They have another test coming up this year, the final test to get ready for the flight hardware. We use this chart to help people understand in a very broad brush term about what's been going on since the replan. It's been a long time. What sort of activities are going on? We're coming out of 2015 when we started the assembly of the mirror. That was the big new thing for this past calendar year. And now 2016 is really the year when these last 3 main elements, the science instruments, the telescope, and then the spacecraft, the final manufacturing occurs and integration really begins on that. And then you can see the 2 things that are coming up in 2017 and 2018. For those of you who like Pert Charts, and hey, who doesn't like Pert Charts, here is another way to look at it. So this is where we are right now. Here we are, January of 2016, and you can see there's still numerous paths along the schedule. We have the telescope being built up. We have the Ison, the Integrated Science Instrument Module under testing. We have that testing and assembly at JPL occurring here, and then the spacecraft and the sun shield at Northrop Grumman. But in 2016, you can see that a lot of these activities down here are actually completing and concluding, and these multiple paths are necking down to just a few paths. And so I'll talk just a little bit about what is going on in this path here, the activity that's at Goddard before we go to Johnson. And through the magic of gratuitous slide animation here, we'll depict once the telescope is populated with mirrors, the aft optic system and the secondary, they install the fixed radiators to the back of the Ison. So those radiators go on before the science instruments come in, and that is the next thing that gets done. They will then flip the telescope structure over, and the Ison gets put into the back, the so-called the backplane support fixture that's behind the primary mirrors. Once the Ison is installed, they integrate a deployable radiator onto the back of the Ison. They then integrate the Ison electronics compartment. The warm electronics are kept separate from the cold instruments, and this is just showing where it gets integrated in the structure. It's kind of down here beneath where they put the Ison in here. Then they connect the electronics to the Ison with some of the, it's a harness radiator, all the wire harnessing goes through here. And now, having built up this beautiful structure, they will stand it upright, do center of curvature tests in the summer. This will be the, right now all those mirrors have covers on them, and so as beautiful it is to see it, it's just black covers. But come the July, August timeframe, they'll stand this up and you will see the beautiful gold mirrors there. And of course, having built this wonderful structure, you then, you bag it and you shake it, vibrate it, and blast it with acoustics, and then do that same center of curvature test again. And it's at that point, around the end of this calendar year, that it will be ready to go down to Johnson for its test in a cryovacuum environment. And so later this year, that schedule will look something like this. So here, I'm not going to read these things to you, but these are some of the highlights of what's going to be going on during 2016. Highlights all across the program. You can see there's a number of big things concluding here in the winter, including finishing construction of the Mission Operations Center at Space Telescope. Many of you know that Hubble is actually controlled out of the Goddard Space Flight Center, but the Institute is going to be flying the bird this time, so that's where the Operations Center is. And so now I actually want to turn to something that this graphic I know will be hard to read, but this was in the October Scientific American, and it was a story about big science. The article that accompanied this graphic was actually about the Human Brain Project, a very large human biology project. And it's a little bit of a confusogram. I'm sure Edward Tufte would be rolling if he saw this, because it depicts the size of different countries and their science budgets, and then some of these things are individual science projects. So here, this is the Human Genome Project here, and the size of the dot reflects the amount of the investment. And there's also a number that says how much is each being put on there. So the largest single science experiment in all of this, larger than some of these countries' investments, is this dot here. It's the James Webb Space Telescope. The American taxpayer, through their representatives in our government, have entrusted us with an incredibly valuable asset. And as Jason mentioned, 2 years from now, the proposals will be due. For about 20 years now, NASA, ESA, CSA, industry partners, folks at the Institute have been running with this baton. And the time for the community to get started to receive this $8 billion baton is now. You need to be moving so that when we go to hand it off, you all are ready to receive it. And I know that there's a lot of excitement for it, and I'm very grateful to see that, but we've been waiting for a long time, but the time to get moving is now. And then this is just a summary of the very successful year we've had in 2015, and what we're going to be doing in 2016. But my bottom line message is we're still on track, we're still on schedule, and we're looking forward to working with everybody here. Thank you.
I'm Neil Reid from Space Telescope Science Institute. I'll be talking about the science policy side of things. I'm representing the science policy group at Space Telescope. That's Janice Lee, who's here. We'll both be here tomorrow morning. Jen Lotz, Amaya Moore-Martin, and then Jason is the contact for science policies in the JWST mission office. So one thing that Jason didn't mention is we're going to post all of these presentations on the web as well. There's some of these slides in here, I've got really dense language. I'll try and step through it carefully. Some of these slides here you've also seen before. From a matter of science policies, it's generally good to say the same thing on different occasions. So some of these will look kind of boring to you, like this one. This one I always like to show at the start because it says what we're supposed to do at Space Telescope. Our goal is to maximize the science return from all the missions we operate. JWST is a mission with a highly complex instrumentation. It's a 5-year lifetime requirement, 10-year goal. It's different than Hubble, shorter lifetime. Maximizing the potential from JWST requires that the community rapidly understands and uses its capabilities. And there's two sides of that I'll talk about here. Early release science program that we introduced last year. We've talked about it at the STEC meeting and so on. I'll go into more details here. And then also, I'll say a bit about the proposal submission process we'll be using for JWST. And just following on from Eric's talk, this is what I showed last year. It's basically what Eric said. JWST is NASA's highest science priority and one of the largest science programs, probably the largest science program ever undertaken by the US. It's up to us now to make sure that it's scientifically productive. So yes, the baton is definitely coming over. So what I'll talk about, some science timelines, some schedule developments in there. I'll talk then about the early release science program, why it's different than your standard GEO program, proposal structure and format, and then I'll talk about the proposal submission process. So the timeline. I presented on this last January and again at STEC. There's a few changes there. There are some points in the science timeline that are fixed. Other things will move back and forward a bit. If you look at the JWST website, this stuff is linked there. So just in terms of the programs that JWST will offer, there are essentially three types. There's the GEO program. 80% of the first 5 cycles will be for GEO observing. Guaranteed observers, these are the instrument scientists, the IDSs, the interdisciplinary scientists, the telescope scientists. They have about somewhat less than 6 months' time that spends over the first 30 months, which is basically the first 3 cycles. I'll talk a little bit about that. And then there's director's discretionary time, up to 10%, so it doesn't necessarily all get used, up to 10% in each cycle, either for rapid response events or sometimes for focused science programs. And I should mention now that the early release science program is coming out of director's discretionary time in cycle 1. So here's the timeline. Here's my version of the timeline. The We Are Here button has been moving, which is good because if it wasn't moving, I'd be dead. The first thing, the fiducial point, several people have said this, November 2017 is when the call for proposals for GEO Cycle 1 is issued. The first proposals that will come in will be from the guaranteed observers. They have a call going out a year from now. The proposal deadline for those proposals is in April, actually April 1st, 2017. And then in June, we'll actually release the list of observations that are being set aside for the GTO observers. And there's a strict duplication policy, just from the point of view you don't want to waste telescope time, that the GTO programs will have priority on observations, and that's observations with a specific instrument for a specific exposure time of a specific target. So one question that comes up is, why is there this gap here between the proposals coming in and then the target list being released? That goes into NASA policy. The GTO proposals go into NASA headquarters. There's 3 things that need to get checked before, when you get the proposals in from these different teams between April 1st, and we've said that June 15 is the sort of drop-dead date for releasing the target list. First, some of the GTOs submitted proposals back in 2000 saying this is how they won time as GTOs. There has to be some kind of consistency between what they're proposing to do now and what they said then. That gets checked by Eric at NASA headquarters. With help from Goddard. Duplication checking, again, you don't want to have the GTOs duplicating each other's observations. I expect there'll be very little there, since they talk to each other quite a lot. And then there's a total time requirement for the first cycle. In the first cycle, GTO time must be between 25% and 49% of the total time available to the GEO community and to GTOs. That turns into something like at least 1970 hours. I'm assuming this is a way of making sure that you don't get hoarding of GTO time into cycle 3. But basically it's saying that about half of the GTO time will be spent, at least half in cycle 1. So once all of these are resolved, we can actually release to the community what the GTO targets are, what the observations are. If we know this earlier than June 15th, we'll release it earlier than June 15th. Okay, what happens next? For the GEOs, the call goes out 2017 November. The cycle 1 deadline is actually a little bit more than 2 years from now, but 2 years is not a big time. The TAC is nominally set for May of 2018, and then observations start April of 2019. Now, some of you might notice that this is an interesting time, May. There's other things happen in May that we're kind of involved with. If you look at the JWST nominal proposal cycle and the HST nominal proposal cycle, there's this kind of collision round about here. Having the HST TAC and the JWST TAC within 1 month is probably going to be difficult to do. So I'm just putting this up to say we're aware that it's bad for us, it's bad for you. If we have proposal deadlines at the same time, you know, HST cycle 26, oh, boring old telescope, what are we going to do there? JWST cycle 1, all the emphasis there. We're going to need to fix that. So we're looking into that. We'll reconcile these schedules by this year, just so that we're aware of it. Cycle 2. So this goes into now as to why we have this early release science program. You're actually going to have to start thinking about Cycle 2 observations after Cycle 1 has barely started. The call for proposals for Cycle 2 is going to go out in September, so that's about, what, 7 months, less than that, 5 months after the first observations were taken. Most observations are going to have proprietary time. There's going to be relatively little data accessible to the community, even at the deadline. And then the TAC for Cycle 2 is in February, obviously before the end of Cycle 1, since you need to know what you're going to observe in Cycle 2 before you start it, as the Irishman said. So this issue here of making sure that the community understands what JWST is capable of is the reason why we have the Early Release Science Program. That's something that the JSTAC, the JWST Advisory Committee, came up with. They noticed this, back in 2010. They pointed out this is an issue. They looked at Spitzer, which are the Quick Look program, as an example of how you can perhaps deal with this by setting aside time early in Cycle 1 for a set of, representative observations using the JWST instrumentation that would be available to the community immediately, so you bring as many people as possible up to speed into what JWST can do, and they can propose for Cycle 2. So that's when we have this concept of the Early Release Science Program, science-driven observing programs designed by the community, selected through proposal peer review, about 500 hours of director's discretionary time. I can now say that we do actually have a director and he is in favour of this, so I can honestly say that there will be director's discretionary time. No exclusive access period, programs selected by peer review prior to the Cycle 1 call. This is the schedule that we're thinking about for the Early Release Science Program. Less than a year from now, we're going to put out a call for letters of intent from the community. Those will probably be mandatory letters of intent. That is that in order to submit a proposal, you have to submit a letter of intent. That's so we could get a good grasp on, letters should say who's the PI, what's the team, project title, short abstract, estimated program size. This is so we can try and understand the scope of what we're going to have to deal with this ERS program. Letters due by February 2017, call goes out in April, proposal deadline August 2017. ERS programs won't be able to duplicate GTO science programs. It's important there's a good separation between this deadline and when the GTO's observing list is made available. The results of this will put out early November, probably, 2017. One advantage of setting up these early release programs before the Cycle 1 call is that we can make these ERS program templates available to the community so that they can use those as templates for their own Cycle 1 GO programs. So this is the schedule then, that's mapping in there. GTO proposals coming in here. Here's the ERS schedule. That is LOI, not LOL. Call for proposals, and then the Cycle 1, and then observations start out here. So one other thing to mention before I get into talking a little bit more about the ERS program, just the GEO program types. This is a slide I showed last year as well. So we'll have small, medium, very large category programs within JWST, similar to HST. Probably in the early cycles, we're going to focus on the small, medium, and large. We're not going to set an upper boundary on the amount of time that any program can ask for, but we won't set aside a separate category for very large programs early on, I think. And I suspect the majority of time, at least in the first cycle, and maybe the first couple of cycles, will be allocated for small programs, very large programs later. And then there'll be specialized categories, long-term programs, TO programs, Treasury Legacy, joint programs. And obviously this is something that we're still working on. This doesn't get finalized until we issue the Cycle 1 call. So what's the difference between an ERS program and a Cycle 1 GO program? When you have a TAC for any large mission, any observatory, basically what you tell the scientists doing the review is find the most compelling science. Everybody has a different idea of what the most compelling science is, but that's the one criterion that you want the reviewers to be thinking about. What's the best scientific use from your perspective of this telescope, this observatory? We're actually looking at something different for ERS programs, because it's not just doing the best science, it's preparing the community to maximize JWST science productivity in cycle 2 and beyond. That means we're looking at issues like addressing technical challenges, putting up science enabling capabilities. So for the ERS proposals, there's an altruistic element in there. It's not just about you, it's what are you doing to help your colleagues. So I've got a few examples of that. This is a scene that may be familiar to many of you. And the appropriate quote is, "Ask not what JWST can do for you, ask what you can do for JWST." I can see people wincing in the audience already. Then from the British perspective, JWST needs you, spelt Y-O-U. And of course, for more modern days, it looks like a Star Destroyer. Okay, but that's why the ERS programs are different than standard Cycle 1 GEO programs. In some ways, they're like it's like a small set of treasury programs, but it really is how are you going to benefit the community and help your colleagues understand how to use JWST going forward. So we've introduced this concept to the community. We put out a survey in October. You should all have received multiple requests to fill that in. Part of that, the reason for doing the survey was to stimulate interest. We wanted to introduce the concept of the ERS program, identify what are the particular interests of the community. I suspect that we kind of know that already, but it's good to get the data. And then solicit input from you guys on what do you see as the support that we need to provide to people who are putting in ERS programs, so we can try and structure that in as well. So far we've got 500 responses, and we're working on collating and analyzing those results. So this is a really dense chart. This is something that went out in the survey, and I'm going to kind of step through it because this is how we define the early release science program, and the 8 different bullets in there. This is also on the webpage. The 8 different bullets there tell you what the program should look like. So the first thing is that it's director's discretionary time with 500 hours, and that's telling you the overall scale of the program. And because it's director's discretionary time, there's no proprietary period, so there's direct community access. ERS programs will be selected to span key JWST observing modes, data analysis challenges, and science areas. Okay, that's the technical challenge part. So we want these programs to actually tell the community how JWST is working. There's obvious challenges that I can think of. There are many more that you can think of. There's crowded field photometry, multi-object spectroscopy in crowded fields, analyzing IFUs, high contrast imaging. There has to be something in there that's going to tell you about the capabilities of JWST. The ERS will be comprised of substantive science-driven programs which have the potential to enable community Cycle 1 archival research and/or be building blocks with which the community can use to design larger JWST observing programs in the future. So conceptually, that suggests a chunky program. Maybe we're talking here about something like 10 to 15, 25 to 75-hour programs. When we're talking about 500 hours, we don't want to split that up into 500 one-hour programs. Apart from anything else, that's not something necessarily we can support well within STSCI. So you're talking about substantive programs here. The ERS observations are going to be amongst the first. There's no point in doing early release science if you don't do it early. So you want to be able to schedule the observations early. That tells you what kind of target selection is going in there. You need to have accessible targets that's optimized for early in the cycle. CVZ targets, as I call them, will be particularly useful. There also may need to be some flexibility in there. You need to take into account some eventuality for things not going quite the way that you hope. So having multiple targets is probably a good idea rather than just focusing on one specific object. If you've got one unique object that you really want to observe, maybe that's better saved as a Cycle 1 GEO program. Another thing is that we actually encourage you, and the exoplanet community have been talking about this already, get together and figure out on your different communities, how do you want to do this? Do this as a collaborative effort. And then finally, ERS teams will be responsible for the delivery of science-enabling products to the community. This is the giving back part, beyond just bringing the data. The delivery timescale should be sufficiently rapid to support community preparations for Cycle 2 proposals. So this is saying that you need to produce data products. So pulling this all together, this is then what you get in the bullets here. ERS programs must address technical challenges of broad community interest. They're likely going to be medium scale. They must select accessible targets, they must have some flexibility, and they must identify useful data products and include a management plan for their delivery. So that's what an ERS program we think looks like. And when it comes to writing the program, the proposal attachment that describes what you're going to do will reflect that. Well, the first section will be the rationale for ERS time, where you're going to need to address the technical challenges and how does this proposal help your community. Management plan, what are you going to produce, what's the schedule for production. Then the scientific justification. Why does the project merit JWST time? We don't want, ERS programs are not just kind of demonstration programs. There also has to be some science backbone in there as well. And then finally, the description of the observations. Okay, so that's the ERS block. Proposal submission process itself. So JWST is at L2. That means that the observation process is basically much more similar to Spitzer than to Hubble. It's not doing orbits. It's event-driven scheduling. We'll have templates available for constructing the observing programs. Observing time is allocated in walk clock hours, not in orbits. That means there's very limited flexibility in adjusting programs after you've been accepted. There won't be the same kind of tweaking within either of targets or of time as with HST. Limited mission lifetime, so you want to have a rapid turnaround. So yes, it's much closer to Spitzer than Hubble. So we're going to adopt a Spitzer-like single stream process for most proposals. There will be exceptions in there, so I'll get into that. What does single stream proposal mean? A single stream proposal is a proposal that's deemed ready for the long-range plan. That doesn't mean it's ready for scheduling. That means that you have enough information that you can look throughout the year and say, okay, here are the windows when I can do these observations. That means you need to know the total walk clock time estimates, including both the science time and the overheads. You need to know all the observations, instruments, filters, exposures, dither, and that's obviously required for the overheads and for the science time. You need the complete list of targets. You need that for the overhead estimates and slews and for duplication checking. And you need the complete set of scheduling constraints, roll angles, timing constraints, linked visits. If you don't have scheduling constraints, that's obviously going to make it easier to schedule. There will be available in APT, you'll be able to check whether guide stars are available. And I know for Hubble, finding guide stars is one of the biggest steps in determining where you put things down in the long-range plan. The plan is that for JWST, you'll be able to do that with an APT in a straightforward manner. And I'd say Klaus is going to explain that, but he won't thank me for doing that. But they will. So, once a program is accepted, they'll all be reviewed before they actually turn into a flight-ready program. So why single stream? It shortens the time between the proposal submission and the implementation. That means there's more data in the archive available to the community because you can put the TAC later in the year. That's really crucial for Cycle 2. It also speeds up the intellectual cycle, more opportunities to react to new discoveries, and there are other issues we're going to look at to speed up this side of things. It enables more rapid and efficient schedule building. I think this actually is, I'm not sure that people necessarily have grasped this yet, but JWST can only see 40% of the sky at one time. That's a substantially smaller field of regard than Hubble. There are also very, very strong constraints on when you can schedule an observation if you want a specific orientation. So I think building that in at the start so you can see at the start what the issues are and you can deal with it is actually going to be a major advantage for the community because we don't want to bring in things that it turns out that we can't schedule. And I will, in terms of the visibility in the sky, we did with Hubble, when we went to single gyro mode, we dropped the sky coverage from, I think, something like 75% down to more like 55%. And that was a significant impact on programs. You had to think things through in a different way. So I really think it's important for the community to understand this going in. Okay, and I guess the bottom also, efficient scheduling is important because the more efficient the scheduling is, the less propellant you use and the longer JWST lasts. So the more efficient we can make this, the better. Implementation. So most JWST programs will be straightforward to implement because we have this template mode now. It won't be the same as with Hubble. There's limited additional information that's required, basically scheduling constraints. APT will have well-documented tools to determine these parameters. We'll also, like I say, have the ERS proposals available as templates to help plan the GO program. And there will be some programs clearly that have to be granted exceptions. If you've got a TOO program and you don't know where the target is, clearly you can't achieve the full LRP-ready state of the program. NIRSPEC MSA observations are probably, that's the multispectral observations are probably the same. Chronographic observations may very well be the same. Large and complex programs. So we'll specify detailed requirements as to which programs should be put in as LRP ready. The other thing is that if it's the last minute and you can't find a guide star, we're not going to toss the program out. Programs that come in at the deadline as non-compliant are going to be flagged, but not disallowed. That's not a carte blanche to make every program non-compliant. And all accepted programs will be reviewed before they're actually scheduled. In terms of implementing this, we can step into this gradually because of the way that the schedule works. And see, cycle 1 will be able to work out a lot of the nits and bumps in this because there's actually 11 months between when the TAC happens and when observing starts. So we can bring in the LRP ready requirements in a staged fashion. Cycle 2, it's more difficult. I mean, I've already shown you this. The cycle 2 TAC we're planning for in February. That only gives 2 months to construct the LRP before you get into cycle 2 observations. And you want to have the LRP constructed as best as possible because you want to go into cycle 2 in an efficient manner. So there will be stronger requirements in the cycle 2 call. And that, I think, is where I am. So we're refining the science planning timeline. There are going to be little shifts back and forward. I think in the flyer that's been handed out, we have something, I guess the ERS call is something like January 2017 and actually February 2017. There are going to be little shifts of a month, but basically this is the template that we're looking at now. We've got a framework for what ERS science programs are going to look like, and I've given you some insight into the submission process. Janice and I are going to be around tomorrow down at the STSI booth. We'll always be around after this. Feel free to ask us questions, and then there's this email here if you want to, JWST_ERS at STSI if you want to do anything. And here's the timeline again to finish with. So thank you.
All right, so I'm Klaus Pontoppidan at the Space Telescope. I'll give you a little update on the status and release schedule for the JWST user tools. The JWST user tools are basically the software packages that you'll need to completely and successfully write, design, submit JWST proposals and observing programs, execute them, analyze the data you get out of them. It's a very large set of software packages, and it's been a years-long effort at Space Telescope, and so we're pretty excited about that. We're rapidly approaching the time when we get to release a lot of these tools that we've been working on so hard. So there's a number of separate packages, some of them familiar to you, many of them maybe. There's the Astronomer's Proposal Tool, APT for short, which is what you use to define your observations and submit your proposals. Of course, there's an exposure time calculator. There are data simulators that you can use to simulate real JWST data products to plan your observations. Of course, there are calibration pipelines that you'd use to reduce your data sets. Of course, very importantly, there is good user documentation. So these are like the instrument handbooks. There are things like archives, and there's also finally data analysis tools, and by that we mean tools that you use to analyze your data after they're reduced. I'm not going to go through all of these, but I'm going to give you a few highlights. Starting from the top, the Astronomer's Proposal Tool should be familiar to HST users. It's basically the same framework we're using for JWST, but there are extensive and important differences as well. So again, this is a tool that you use to define your JWST observing programs and submit your proposals. You can actually already see the development versions of the JWST APT because it's bundled with HST APT, and you just, instead of starting a new HST proposal, you can start a new JWST proposal, and you can see what's in there. And of course, you can find that at this web address. So as Neil was talking about, the submission process is a bit different for JWST, especially to make the process turnaround times faster. And so that also requires that the tools enables users to more easily define their observations. So the APT will define JWST observations using templates. And so what do we mean by that? Well, similar to Spitzer and Herschel, you have certain observing modes and strategies that define a template. And so examples of those can just be something as simple as, say, MIRI imaging, near-spec IFU, near-cam coronagraphy. It can also be sort of a little bit more abstract, things like time series observations. And here you have an example of a template for near-cam coronagraphy. So the point of having a template is that instead of specifying your observation in every single detail, it only requires the necessary information that is needed to fully define an observation. And so basically, users will not specify every single exposure they're taking. They'll fill out this form, and then APT automatically splits an observation as defined by a template into individual visits, a visit being an observing sequence that uses a single guide star. And within a visit, you can have multiple exposures as well. So a lot of this is automated now to make the process easier. Then there's the exposure time calculator. Exposure time calculator is a new system that doesn't have anything directly in common with the HST exposure time calculator. We call the ETCIE System Pangaea. Pangaea is a minor Greek goddess, the daughter of Selene, the goddess of the moon. Pangaea means all brightness. So we thought that was appropriate. It's the ETCIE system is a very modular system, right? So it has a component that consists of the reference files for the ETCIE, which means throughputs. There's point spread functions in there that are actually calculated using optical models, using WebPSF, which is another tool, and the noise parameters. There's an engine, which is a general data-driven Python library that's not specific for JWST, so you could apply it to other observatories and instruments. There's a server, which allows you to store your calculations, so you can make many ETCIE calculations, come back and look at them later, or share them with your collaborators. There's a user interface, which is a web application with a lot of functionality. I'm going to show you a little bit more about that. The release schedule for the ETCIE is that we're planning to release the ETCIE engine, so the Python library, along with the reference files, as soon as we complete the verification of the ETCIE, and the verification being we benchmark it relative to independent ETCIE calculations from instrument teams. And we're planning that in just a few months. The web application will be released no later than January 2017, so that will be the flight release for that. Of course, after the release, we're going to continue to develop these tools. So this is an example of, so there's a little movie here. So this is the ETCIE web application. We have multiple workbooks. Each workbook can contain a number of ETCIE calculations. And all these ETCIE calculations is hard to, they can be for different instruments, different observing modes. The ETCIE will create scenes. Here you actually have multiple sources in this scene. You can extract signal from a scene and plot it as one-dimensional plots. Here you can see for the same scene, you can look at both imaging observations as well as this is a near-spec slitted observation of that scene as well. And you can also plot multiple calculations here on top of each other, so that in the one-dimensional plot here, for example, you can compare signal-to-noise ratios of multiple calculations. So we're trying to make it easy for you to make parameter studies or grid searches to find optimal observing solutions. And there are many different input parameters that you can change here, both in terms of how the background is calculated, how the instrument is set up here. Also how you extract the signal, and whether you use aperture photometry and some other way to extract the signal-to-noise ratio. Okay, so the ETCIE is not necessarily an appropriate tool for all performance estimations. Because we're trying to make it fast, so you can do this kind of parameter studies, the ETCIE only calculates performance on a little postage stamp, a few by a few arc seconds in size. So if you want to simulate a full near-cam field of view, you need one of the simulators. So we have a tool called the Space Telescope Image Project Simulator, or STIPS for short. This is a tool that you can use to input much more complicated scenes and much more complicated observing sequences into the patterns and get the full field of view. It's a web tool. Right now, the initial release will include the JWST imaging modes, and it also includes several astrophysical models, including stellar populations and galaxy populations. We plan to expand these things here, and we're planning an initial release this year, probably relatively soon. So in order to use these tools efficiently, of course, we also need good documentation. So that both includes a new website as well as a new documentation system. The JWST website is going to include higher level mission information as well as JWST science content. The new documentation system is going to be quite different than what you're used to from instrument handbooks. We're using a philosophy called Every Page is Page One, which is a book by Mark Baker. And basically, the idea there is that instead of having this really, really long document, you have many short articles. And each article has a very self-contained scope. It has information at a single level, right? So it can be a very technical article, it can be a very high-level article, but it doesn't try to mix the two. And then you have a very extensively hyperlinked network rather than this monolithic document. And so you can sort of, when you're searching for information, the hyperlinks makes it easy to find exactly the information you need. Of course, this is all Googleable. So basically what you need to think about is something like Wikipedia, except it's not a wiki, right? But the same kind of style is what it's going to look like. It will also have multiple conceptual spaces, right? So you can have, for example, background articles, planning cookbooks, science policy documents, as well as very detailed engineering specs. So all be within this system. For the documentation, we're planning incremental releases, basically as articles are written and reviewed. And right now, we're actually already reviewing articles to be used for the first proposal planning, so things like instrument articles, articles in APT, as well as ETCIE articles. So let me switch gears a little bit and go to the end of the process. Right? So this is an area that has seen a lot of recent development, and so this is the suite of data analysis and visualization tools. And so we're making a lot of new tools that modernize a lot of things, as well as tries to create tools that address many of the complex observing modes of JWST, such as IFUs, for example, multi-object spectroscopy. The JWST data analysis tools will be are in Python and AstroPy. Basic capabilities are familiar with users of IRAF, other tools, but there'll be much more. And visualization will be done in Ginga and in Glue. Ginga is an image viewer, and Glue is a system for combining data in databases. And I'll show you an example of how this works. The tools understand JWST data structures and all their metadata, including data associations, for example. This is also an important point. This is an open source effort, so you can actually see what's going on at any time, given using this web address, and you can actually use the tools already, although they're of course very extensively being actively developed at the moment as well. This is the schedule for the data analysis tools development. Right, so we're right here right now. This is the AAS. As you can see, in the next couple of months, they'll be working on PSF tools. They'll be working on JWST data file, I/O, and associations. There'll be more development on a one-dimensional spectral tool called SpecView. So they already exist, and you can already try it out, and so on. And then there's a lot of other things planned. All of these things are done in short sprints using the Agile Philosophy for software development. So this is a movie of one of the data analysis tools used for IFUs, as well as SpecView. Goes a little bit fast here, but you can get an idea of how workflows might work, right? So you take a data cube, you can load it in to the tool, and then you get this IFU cube. You can move through wavelength slices here. See this galaxy at different wavelengths, and then you can also cut out parts of the galaxy and show it as one-dimensional spectra. Here you get the whole full cube as a one-dimensional spectrum. Or you can drag out a region here, and then you get another spectrum, and you can compare them in the same plot. And again, you can drag out complex regions in the field, and again compare that in the plot. And then once you have everything in the one-dimensional spectral viewer here, you can pull this up here and then zoom in on the lines, and then do a detailed line fitting using the SpecView tool. So using a different tool. So things tend to be combined in a very extensive way, supporting different kinds of workflows. So this is just an example. The timeline for user tool releases. So right now we're here in 2016, the 227th AAS. So the next thing that's going to happen in terms of big releases is that it's the ETCIE engine release. So this is a development release, but it'll give you the first chance to see what the ETCIE actually does as a Python library. So it requires a little bit of Python knowledge, but otherwise you'll install it as any other Python module. After that, we'll have the first, during the summer, late summer this year, the first incremental user documentation release. And then around the turn of the year, we'll release the ETCIE web application, the one to be used for Cycle 1 planning. So that'll be during the 229th AAS, so not in summer, but next winter AAS. And then a little bit later, there'll be the APT flight release here. And here you can see the early release science deadline in the Cycle 1 call for proposals. So we also plan various types of workshops and meetings to help you all use the tools, give you training in them. Right, so as Jason pointed out, we just had a meeting at STEC. We'll have another one this fall in Canada, and as part of these big meetings, we'll arrange events and workshops to introduce you to the tools and give you hands-on experience. We'll also have topical science meetings at the continuous we've had in the past at Space Telescope. So this will be science-focused, but as part of these science meetings, there will be an element, again, of user tool training. So we'll do that as part of these things. We also have sort of specifically focused user training annual workshop at Space Telescope and AAS. We had some on Monday as well, so you've seen a little bit of it. And as going forward, we'll continue to host that. There's also a JWST Colloquium series, so contact us if you'd like a a general presentation about JWST as well as a user presentation at your institution. And there's a plan to make community days, which is an open call to US institutions to host hands-on JWST one or two workshops with an optional science meeting. And again, it's planned for observing. So thank you very much. I'll leave that up here and go to Science Talk.
It gives me great pleasure to have the opportunity to discuss with you and share with you a status report on our current understanding of the formation of the first black holes, and in particular, what is really exciting in the recent progress that we've made in the theoretical modeling of the formation of these first objects is that JWST turns out to be a very crucial and critical set of instruments that can answer some of the basic and most fundamental key questions about the growth, the formation, and the growth of the first black holes in the universe. I have here acknowledged the work of many groups and people over the last 5 to 10 years because there's been tremendous progress in our understanding. Of course, there's been a lot of work over the past couple of decades on understanding the growth history of accreting and quiescent black holes locally. In particular, now we understand quite well that locally there appears to be a relationship between the masses of black holes and the properties of the stellar bulge, the luminosity of the bulge, and the velocity dispersion of the bulge that hosts that black hole. So these studies have demonstrated that there are correlations between key quantities. So for example, there's a correlation between the bulge mass and the black hole mass, bulge luminosity, stellar velocity dispersion at low redshift. So the obvious question is, what is the origin of these correlations and whether these correlations actually are set up at high redshift if there is some physical basis to these correlations beyond just the merging hierarchy that you expect in the lambda CDM paradigm. So when one looks at what the open questions, as I mentioned earlier, it's going to be pretty obvious to you from some of the calculations that many groups, including mine, have done over the last few years, that some of these important questions, JWST actually offers a way to really understand and discriminate between current models that we are playing with. So obviously the first key question are the masses of the initial seed black holes that form in the universe, the earliest seed black holes. And of course, once you form the seeds, the accretion history of these black holes, whether it's somewhat different from the accretion history that we observe for black holes at redshifts 3, 4, 5, and 6, which have now been detected, not just as few random objects, but as populations. We understand them quite well. So, and as I said, one of the driving questions is whether these correlations, what are the physical basis, whether there's a physical basis for these correlations, and when they actually get set up in the universe. And of course, related to that are many other subsidiary questions, as the importance of mergers in feeding black holes, the contribution of potential early black holes to reionization, because there appears to be a little bit of room now from the latest Planck results, and of course the big theoretical understanding has been in our sort of ability to simulate super Eddington flows. So the question is, what are the accompanying observational signatures, and if any of those would actually become available with JWST. So I just want to mention here that a lot of the work on these early black holes has been supported by a new grant scheme called the TCAN. In fact, 3 independent groups and 1 including that I am part of were funded to really investigate issues of black hole physics. So this has been a real area of theoretical progress most recently. So the specific questions that are of interest as I mentioned, are how do black holes and their host galaxy actually know about each other, and whether the scaling relations actually evolve through cosmic time. So at the moment, we don't have any empirical evidence for the redshift evolution of these correlations that I showed you at redshift 0. And of course, key to understanding the origin of the first black holes are the initial conditions and what really shapes the initial masses of the seeds. So we actually know from multi-wavelength data at the present time that we have a lot of evidence for the properties of active as well as quasar black holes. So one interesting feature for the last decade has been the discovery of supermassive and ultramassive black holes, so bright quasars powered by very, very massive black holes in excess of 1 billion solar masses at redshifts greater than 6. So in fact, the record holder is almost 10 billion solar masses at a redshift of 7 when the universe was incredibly young. So the question is, if there is a population of such massive black holes already in place when the universe was so young, then the seeds in turn have to really be quite massive given that there's a real timing crunch to assemble them. Of course, in lambda CDM, you can have a few freaky objects, but the problem is when you have an entire population. And it appears that there is an entire population of very massive black holes in place extremely early in the universe. Now, the solution to this problem has been the suggestion that you make very, very massive initial seeds. So the conventional wisdom was that you made the first population of stars, population 3 stars, and their remnants would give us seeds, but it turns out that recent work, recent refinements in numerical simulations show us that the seeds that you would get from population 3 stars would be of the order of 10 to, say, 100 solar masses. These masses are too small to account for the growth history within less than a gigayear of the most massive black holes that are powering the quasars that are seen at redshift, so 6 and beyond. Therefore, the model, a competing model, which has been proposed in many different guises for a very long time, is this idea of direct collapse black holes, where basically you circumvent the formation of the first stars, you suppress cooling, and you directly form a very massive black hole seed with a mass in the range of 10 to the 3 to 10 to the 5 solar masses. And of course, this is in protogalactic halos, so there's no enrichment, extremely high redshifts. So basically, it looks like we not only need many different ways to make seeds, but that most likely, at least there are these 2 sets of mechanisms by which we can make seed black holes. Now, the properties of these seed black holes are somewhat different, both in terms of their growth history and in terms of the kinds of correlations that would get set up in the host halo in which they form. So before you get carried away that we really understand how these either POP3 remnants form or these direct collapse black holes form, I just want to remind you there are still uncertainties. So for example, our current understanding for the mass distribution of POP3 stars from simulations suggests that there is sort of a mass range. We don't quite know the full IMF, but it looks like this is the mass range of the stars themselves. And then we're talking about the remnants from these stars. So recent progress in simulations has suggested that you probably form a cluster of population 3 stars rather than single massive star as originally believed. So you would actually have a cluster of remnants. So you could end up having a lot of light black hole seeds that eventually coalesce and form a more massive black hole seed. And how does one distinguish in this scenario between these light seeds that coalesce versus a direct collapse black hole seed? Once again, it's a question of timing. So if we can access very high redshift accreting black holes, then we can actually move towards settling this question somewhat. To add a little more complexity to this problem theoretically, we also find that there are ways in which you can super boost the growth of a single light seed in one of these nuclear star clusters. However, there are very, very specific accretion signatures associated with each of these scenarios, which are now calculable. and which many of us have been calculating and have found that they can be discriminated at high redshift. And one of the key ways to discriminate them is to understand what happens when you form a direct collapse black hole. You form a direct collapse black hole at very high redshift in a metal poor halo, in a pre-galactic metal poor halo, where you bypass the formation of stars. And the way you do that is you photo-dissociate all molecular hydrogen from Lyman-Werner photons from a nearby halo. So you have a satellite halo is the most likely place where you form the direct collapse black hole. So you see that we already have some understanding of the spatial distribution of where the first black holes are likely to form that allows us to discriminate between population 3 versus direct collapse black holes. So what we find now is that these direct collapse black holes form in satellite halos, so you have another stellar population in the vicinity. And since this direct collapse black hole has a mass of 10 to the 3 to 10 to the 5 solar masses, there will be a certain stage during which the black hole dominates, accretion onto the black hole dominates the stellar component, okay, that assembles. And that is key. And this is precisely what JWST can help us discriminate between. So what is shown here are the kinds of black holes that will populate a putative black hole mass, stellar mass relation, where you have these new kinds of galaxies, a new population of galaxies, which we have termed as obese black hole galaxies. They contain black holes that are overmassive compared to what you would expect with, given the local correlation between black hole mass and host halo properties. So we have, theoretically, we can predict as a function over redshift how these direct collapse black holes that are hosted in these obese black hole galaxies would actually track and follow the M-sigma relation. So it turns out that some of the key properties are that the star formation is initially inhibited in these halos because of this photodissociation, and you would therefore have pretty much every quasar that you see, bright quasar that you see at redshift 6 or so, would have transited through such a direct collapse OBG stage. And so detecting these, a population of OBG galaxies would actually ratify the massive seeding model for the first seeds. And so what is interesting about these obese black hole galaxies is that you will be dominated by the spectrum would be dominated by accretion onto the black hole. The UV spectrum would be lambda to the power beta, where beta is about minus 2.3. And typically, you would have the absence of a Balmer break. They'll be spatially unresolved, and they're expected to be brighter than the majority of high redshift galaxies. Of course, you also expect broad excitation lines, and that depends on the chemical enrichment history of the galaxy, and these are all calculations that are currently ongoing. So what is shown here are the observability of these obese black hole galaxies computed for JWST for a signal to noise of 10 for 10 to the 4 second exposure. And the NIRCam detection limits are shown as circles and MIRI are shown as squares. And so essentially, if you have this direct collapse black hole accreting at Eddington or super Eddington rates, you will not see a Balmer break, and you would actually be able to detect most of these sources. Okay, and so there are theoretical models that we now have where we can predict the evolution of such sources, the OBGs, as a function of redshift. And so this is just this is a simulation from of an OBG candidate in a very small box from a simulation called The First Billion Years, performed by Sadek Kochfar and his groups. So what we've done in terms of the analysis of the properties and detectability by JWST is we've sort of looked at the size magnitude distribution. As I said, the bulk of these objects will be unresolved and they are likely to be brighter than galaxies. So a very, very important discriminant between seeding models. Of course, there are signatures of seeding models that persist down to low redshift, but catching these very distinct signatures at high redshifts would really help us understand how the most massive black holes in the universe assemble. It appears like the most massive black holes at any epoch, starting redshift 6, the detected quasars at 6, all the way down to redshift 0, require a slightly different accretion history and slightly different seeding model in order to explain the data that we currently have out to redshift 6. So in conclusion, let me also show you what the minimum bolometric luminosity would be, that would be required for a quasar at some given redshift to be detectable by a JWST filter. So what we find is that direct collapse black holes, which are going to be more massive black holes compared to the POP3 remnants at redshifts even down to from 10 all the way down to 6. So all these accreting quasars with luminosities in excess of 10 to the 7 solar luminosities will actually be detectable by NIRCam. So if the direct collapse channel is one in which a large fraction of the progenitors of the most massive black holes pass through, then we would actually detect them fairly easily. And to compute this, we've just used, at the moment, we've used a very standard quasar template, which includes the emission lines and so on. And we've used Jane's table of JWST sensitivities. And so and this has been computed for Eddington accretion. As I said, we now understand a lot more about super Eddington accretion, and calculations for the observability of sources accreting at super Eddington rates are ongoing at the moment. But even at the Eddington rate with 10% efficiency, essentially it looks like a direct collapse black hole with a mass of 10 to the 4, 10 to the 5 solar masses should be detectable by JWST. Now, the question, of course, the other difference between these two seeding models arises from how they actually progress on to correlations that we see at lower redshift. So in the case of massive seeds, there is a lag in the assembly of the stellar component because the black hole is overmassive before the black hole can land on the M sigma relation at redshift 0. So let's see if we are able to therefore detect sources, these direct collapse black hole sources, these OBGs, at various redshifts, at high redshifts from 10 to 6 using JWST, then we actually have the possibility to discriminate also the way in which such correlations could be set up. And so how the mass of the seed, the mass of the initial seed actually determines how you fall onto these correlations, how you evolve onto this correlation, all the way from redshift 10 out to redshift 0. And the detection of these OBG candidates, you'll see that the way in which you come onto the correlation is markedly different. And if we are able to detect sources in different redshift slices, we'll actually be able to nail down some of the accretion physics and the growth history of black holes as well. So let me just conclude with a slide that is clearly showing you what the two competing models are at the moment and how JWST observations, as I've shown you, can actually help discriminate between these two possibilities. So the two possibilities are massive initial black hole seeds set up at very high redshift, and we're talking redshifts of 20 to 15, as opposed to population 3 seeds, remnants, which are less massive. And these seeds could also have super boosted growth, which would again be detectable, super Eddington growth that would be detectable with JWST. And of course, I have not mentioned here what NERSPEC can do, because this is still work in progress. We've just been working with toy spectra. We haven't really made concrete predictions for NERSPEC quite yet. In fact, what would of course be awesome is if, along with JWST, there was also a large field of view X-ray surveyor in space at the same time that would actually nail down a lot of the growth history as well as the physics of the initial seeds. So I'll just stop here. Thank you.
Okay, that was great. Thank you so much, Priya. It's an exciting new science opportunity for JWST. We're going to do questions. So as you think of your questions, just 2 quick announcements that I forgot. One is that some of the information that was on Neil Reed's slides, the early release science program, the science timeline, if you want a concise summary of that, we have some nice flyers at the Space Telescope Science Institute booth. So please come by and pick one up. And the second thing is we could only squeeze one science talk into this session, but you can see the tremendous excitement for new science opportunities with JWST. There's JWST science throughout the AAS meeting. One session that I'd especially like to point out is a session tomorrow that the 30-meter telescope group is organizing on mid-infrared science. That includes some synergies between TMT and JWST for mid-infrared astrophysics. Okay, so do we have any questions for any of the speakers? No? Last chance? Okay, if you want to talk to any of the speakers personally, feel free to come up. I'll ask them all to stick around for a few minutes. And thank you, everybody, for attending the town hall.